Section 7.3 we'll be learning how to solve multivariable linear systems. And these, unlike our previous systems, will have more than two variables. Typically we'll be dealing with three, but you can use these techniques to solve for systems of any number of variables as long as they are linear systems. That means there are no variables squared or square rooted or anything like that. To solve them, we're going to use a form of elimination called Gaussian elimination. But we'll get to that in a minute. First, let's take a look at this system here. It's fairly simple as such systems go, because here, see, we already have z solved for. So how to go about solving this is pretty straightforward. We know that z equals 2, so we can take that z value, plug it into the next equation up, solve for y, and once we have y and z, we can plug those into the first equation to solve for x. This is called back substitution. So let's go ahead and run through this. Z is 2. This second equation gives us y plus 6 equals 5. So y equals -1. And then we can plug these both into our first equation to solve for x. So x minus 2 times -1 gives us plus 2. Our z is 2. 3 times 2 plus 6 is 9. X plus 8 equals 9, which gives us x equals 1. So the solution to this system of equations is the ordered triple, not an ordered pair anymore because there are three variables. It's the ordered triple 1, comma, -1, comma, 2. And as you would expect, the first value is x, the second value is y, and the third value is z. Now that was pretty simple. So what we're going to do when we have a more general linear system is we're going to try to get it in this format, where one equation has all three variables, the other equation has no x, but it does have y and z, and our third equation has z already solved for. Or if you have more variables, just make one variable in the bottom equation, 2 variables, 3 variables, 4 variables, 5, and so on up. When a system is in this format is called Row-Echelon form. Right. Now, let's take a look at a system that's a bit more complex, one that is not already in Row-Echelon form. When we have a more complicated system to solve, we are going to use elimination to put this system into that Row-Echelon form that we saw in our original simple example. That elimination is called Gaussian elimination. And the only reason that I care about I guess there's some glare there. Gaussian elimination. Woo! Alright. The only reason I care about you knowing that it's called Gaussian elimination is because the book will say use Gaussian elimination to solve this system. So you need to know that it means this method of putting that system into Row-Echelon form. Now in order to simplify what I have to write down here, I'm going to call this the first equation, equation 1, the second equation, equation 2, and the third equation, equation 3. And that notation will just make writing out our solution to this system simpler. So if you remember, our Row-Echelon form for a 3-equation system had all 3 variables in the first equation, only y and z in the second equation, only z in the third equation. So let's start off by dealing with equation 2. Now we want to have only y and z in this second equation. So that means we need to get rid of this negative x here. Whatever x term you have in the second in the second row you're going to want to get rid of. And you're going to get rid of that by adding some multiple of the first row. In this case, x plus negative x will get us 0, so we can simply take equation 1 plus equation 2. Taking equation 1 plus equation 2, x plus negative x is 0. Negative 2y plus 3y gets us y, and 3z plus 0 gets us 3z. And 9 plus negative 4 is 5. So now we can replace the second row of our equation with y plus 3z equals 5. Y plus 3z equals 5. So row 2 is now in the proper format. We want to get row 3 into the proper format, meaning we want to get rid of x and get rid of y. Just as we did for our second equation, we will get rid of x using the first equation. This is a 2x, this one has just an x, so to get rid of x in our third equation, we need to multiply equation 1 by negative 2, and then add it to equation 3. So we're going to take negative 2 times equation 1 and add that to equation 3. So negative 2 times equation 1 is negative 2x plus 4y minus 6z equals negative 18. And then to that we are going to add equation 3. 2x minus 5y plus 5z equals 17. Negative 2x plus 2x is 0. 4y minus 5y is negative y. And negative 6z plus 5z is negative z. Negative 18 plus 17 is negative 1. So now we can replace equation 3 with this new equation we've just found. Negative y minus z equals negative 1. But we're not quite done yet. We still have one more step to go before our system is in row echelon form. And in that step, we need to eliminate the y from our third equation. And we're going to do that, in general, we're going to do that by adding some multiple of equation 2 to the equation 3. In this case, y plus negative y will already cancel out our y's, so we don't need to do any multiplication. We simply take equation 2 plus equation 3, and that will eliminate the y in our third equation. I'm going to make some more space down here. So we take equation 2 plus equation 3, and that yields 0. 3z minus z is 2z, and 5 plus negative 1 is 4. When we get to this point, rather than writing 2z equals 4, we'll just do a quick simplification. We can divide both sides by 2 to get that z equals 2. Once we have this, we can replace equation 3 with that same equation. Now, if you're paying close attention, you might notice this is the same system that we started with in our simple example. So I can already say from before, I know that the solution to this system is the ordered triple 1, negative 1, 2. If we go back, our original system, this is the row echelon form. This is the row echelon form of our system. Our original system was x minus 2y plus 3z equals 9. So we can check, that was our first equation, we can check this in our original equations. This equation was already here. So that's 1 plus 2y plus 6, 1 plus 2 plus 6 is 9. Our second equation originally was negative x plus 3y equals negative 4. If we plug into this equation, we have negative 1 plus 3 times negative 1 is minus 3 equals negative 4. That works. And our original third equation was 2x minus 5y plus 5z equals 17. If we plug those in, we have 2 plus 5 plus 10 equals 17, which is indeed true. So this ordered triple, just confirmed, solves our original equation, our original linear system of 3 variables. Just one thing to note, the advantage of doing this on the whiteboard is that when I perform an operation, I can just erase one equation and replace it. When you're writing this out by hand, it does take up a fair amount of space. So be warned that there's a lot of writing involved in solving these problems.